Okay, so I'm Michele Lombardi. As Riccardo said, this is John Michele, also from University of Bologna. The topic is, I'm going to talk about a conflict detection algorithm for precedence constraint quotient. So let's start with some context. Say we have a disjunctive scheduling problem like this one. We have this graph, we have unary resources, some of the activities require the unary resources, say those guys are requiring the same resource, which means that we have conflicts. And each conflict will be, of course, associated with a pair of activities requiring the same resource and not ordered by a precedence constraint, either direct or implied. So this is a conflict, and this is another conflict, and so on. For each of those pairs, in order to build a solution, we have to take some decisions. We can either fix their start times, and we do like this, or we can take an ordering decision and just add a precedence constraint. So I'm interested in this second case. There are some reasons why one would be willing to do this. And for example, if you do this, you get smaller domains. You just reason on ordering decisions, which are basically Boolean variables instead of a bigger one. So this is good for some search heuristics, for example. You naturally get a flexible schedule. Enforcing temporal consistency is relatively easy in this kind of problem, so you can adjust your schedule to what happens at runtime, which also means that you have a very good support for uncertain durations or for decision on the dependent durations. So there are a number of reasons why this stuff is maybe interesting. So then the question I'm gonna try to answer now is it possible to apply this stuff to cumulative scheduling as well? And it turns out it's true. Consider a set like this. You have A6, A5, A6, and A2. I'm assuming the capacity is 2, so this is now a cumulative scheduling problem. So let's look at this set. Those three activities, they are not connected to a precedence constraint, so they can overlap in time. If they do overlap, they will cause a resource overusage. If I remove even a single activity from the set, the overusage is no more. This kind of thing, a set like this, is called in the literature minimal critical set or minimal forbidden set in the OR papers. Why is it interesting? Because it shares an important property with the previous set. The important property is this one. You add a precedence constraint and the critical set is no more. You have prevented the conflict. So this immediately suggests a possible search strategy. We can solve the problem by iteratively selecting a conflict set, selecting a pair of activities from the set, and posting a precedence constraint. Then we enforce temporal consistency, and we keep on, we repeat this process. On the track, we just negate the constraint that we have posted on the left branch. We stop the process when we can find no more minimal critical set. Why? We know that temporal consistency is enforced, right? If there are no more minimal critical sets, it means that our schedule, the graph that we've been building so far, is also resource feasible. There is no possible conflict. Okay, so a schedule like this, which looks like an augmented graph in practice, is called a partial ordered schedule. Okay, so the tricky step in this strategy is this one, how to select the MCS. And there are several ways that tell you how you can do it from the literature. I will focus on two of them because they are, as far as I know, the state of the art for their class of generality. Meaning that unless you plug in some more information in your strategy, that is more or less the best you can do. So the first one is very simple. You can enumerate the subsets. Obviously, you don't want to enumerate all the subsets because this is going to take forever. So what you do, you try to be smart. You exploit the precedence constraint. You don't want to put in the same set two activities which are linked directly or indirectly by a precedence. So you can use that stuff for pruning. You can do more. Usually you just don't look for a minimal critical set. You look for a minimal critical set which is good with respect to a selected ranking heuristic. And you can exploit this ranking heuristic in order to compute bound and prune some nodes from this enumeration tree. So in practice what you do, you run a branch and bound algorithm and you find the best minimal critical set according to your heuristic of choice. The good part of this approach is this, that you have the best MCS, at least according to the heuristic. The obvious drawback is that we have the worst case complexity is exponential. There is no escape, no way to escape from this with this kind of approach. There is another very interesting approach in the literature which works in a different way, in a different fashion. It's more or less like this. We look at the graph and we build time windows with reduced time windows and activities. We can do it by reasoning either on possibly present time windows themselves or on the precedence constraints. So then we look at the earliest start time of each activity and at the latest end time of each activity. For each of those points, we compute the maximum possible resource usage. This can be done by applying a sequence of graph transformation and obtaining a sort of a dual graph. Then we run a maximum flow problem on this graph, and this gives us two things. The first one is the maximum possible resource usage value at the considered event, corresponding to the considered event. The second thing is the subset of activities which is causing the maximum usage, right? So why do we do this and not something simpler? Because in computing this resource usage, we must take into account the precedence constraints. So we need some slightly more complicated mathematics in order to get this. Okay, so at this point of time we have marked on the time horizon all the earliest times and all the latest times. We know the maximum possible resource usage for each of those points, and this stuff gives us a maximum usage envelope. This curve tells us what is the maximum possible resource usage at every point of time. So the next thing we do is take the peaks, that is the points where the maximum resource usage is above the capacity. Each peak corresponds to a subset of activities which is exceeding the resource usage, but is not necessarily a minimal critical set, because it may not be minimal. In order to get a minimal set, we can do enumeration, for example. We enumerate a little bit. Obviously this will be much faster than previously because we are considering a smaller subset, and in order to be even more fast, we stop after considering a few MCS. So we try to contain the complexity in this way. So what is good about this? It is much faster than the previous algorithm. Still, it examines a lot of critical sets and finds very good quality ones. The exponential work case is still there, however, because we are enumerating on this subset. So we may spend some time looking for subsets here. And another big point is that it is not trivial to implement. The graph transformation that I told before, you can do them, but it takes some time to realize all this. Okay. So I told you there are other ways to look for minimal critical sets, but you have to make some more assumptions. For example, to have a regular cost function or something like that. Okay. The question is this. Is there something which is truly polytime in order to solve this problem? And perhaps something which is even easier to code than what we have said so far? The answer is, well, actually, you can do it, and this is the first contribution of this paper. Let's start from this. If we are solving a scheduling problem like this, odds are that we are storing somewhere a simple temporal network. Okay, now we do something a little bit weird. We label the arcs in the simple temporal network that correspond to the original activities with the resource requirements. So we get a graph made more or less like this. Now we view those requirements as flow demands. And we consider the problem of routing a flow from here, from the source of the graph to the sink, such that all the demands are satisfied. This is one such feasible flow. We have 5 units here, we split in 3 and 2, we split again 2 and 1, we have those 2 here, and of course we have 5 at the end again. Right? Okay, this flow is feasible, meaning that it satisfies all the demands. It is not a minimum flow that satisfies all the demands. If we want to look for the minimum one, we start looking for diminishing paths. Those are paths in the graph where we have an excess, we can detect that we have an excess of flow. In this case, this is a diminishing path. If you look carefully, we have always more flow than needed throughout all the graphs, all the arcs on this path. In particular, we have one more unit, which means that we can decrease the flow on this path by exactly 1 unit, and we get this. So now we have a minimum feasible flow, and we can compute this. This procedure I'm showing to you is just a standard or algorithm, just inverted. Usually you do it for maximizing flow. Now I'm using it for minimizing flow. Okay, now we have the minimum flow. What is the nice thing? If we look at the separated arcs, they always form a cut in the graph, meaning that they split the graph in two parts. In this case, those are saturated. The flow passing through this arc is exactly equal to the demand. This cut corresponds to a subset of activities. In this case, they are A5, A6, and A7. Okay, the nice part is that it can be proved that this subset of activities is the subset causing the maximum possible resource usage, obviously taking into account the precedence relations. Okay, now we can get this very efficiently using the algorithm I told you before. So now there are two possibilities. Either this maximum resource usage does not exceed the capacity, in which case we are done, we have a solution, or it does exceed the capacity, in which case we have a critical set, not necessarily minimal, and we still need to minimize it. We can use enumeration, of course, as before, but we can also do something simpler. For example, we can do some greedy minimization. This is what we try to do. We use a field primary procedure. We remove activities from the set, and we always look for the activities that yields the subset with the best ranking according to a selected heuristic. So what is nice about this novel method? First point, it requires no graph transformation. You have no overhead here because they are running the algorithm basically on the simple temporal network. It is easy to implement. You don't need just a few leads or a few more data structure, and the algorithms themselves are very easy. The flow minimization can be implemented in a couple of loops, and the greedy minimization are the same. It is fast because it does not have, well, it is a pseudo polynomial in principle, but in practice it is very, very, very efficient. We can consider it to be polynomial. Finally, and this is very important, this kind of approach is very well suited for constructive search. If you are building a schedule by resolving one conflict at a time, when you solve the next conflict, you will always have the optimal flow from the previous step. The optimal flow from the previous step will be very close to the optimal flow in the current step. So we just need a couple, 1, 2 diminishing paths in order to merge together. This makes the computation very, very fast in practice. The obvious main drawback is that since we are analyzing a much smaller number of minimal critical sets compared to the other approaches I showed to you, then perhaps the critical set that we are going to select is not very good for branching. How do we know it? There is only one way. We make a big experimentation, and this is the second contribution of this paper. We took the PSP lead. We used exactly the search strategy that I showed to you, where I branch on the minimal critical sets. We used for the ranking heuristic the preserved space, which is very common, which is quite accepted in the literature. We used some constraint propagation, temporal consistency of course, and some resource propagation, timetable and edge finding in particular. And we put a 600 seconds time limit. So here is how the results you will see look like. We have a bunch of columns. Each column represents the average for 30 instances. And we are grouping instances in the PSP lib according to their resource factor and resource strength. Basically, if you go in this direction, you are increasing the resource contention. If you are going in this direction, you are increasing the amount of each requirement. Which means that if you turn like this, you will have bigger minimal critical sets. And if you turn like this, you will have many critical sets. Okay, so now the results. This is the number of optimal solutions obtained with the 3 approaches on J30. In this case, we have 30 activities in each instance. And as you can see, unfortunately, they are a bit darker, but the NO approach is the best here. It's finding solving optimally the highest number of solutions, and the mean flow is the worst. The envelope is something in the middle. If we move to J60, where the instances are bigger, 6 activities, the picture starts to change. The mean flow, of course, got a little bit worse because we were scaling up, so no surprise here. But the interesting thing is that the enumeration starts to have a lot of difficulties with this corner. You see the columns are getting brighter and shorter. And the envelope approach is a sort of a sweet spot, in particular for this benchmark in particular, because it provides a very good compromise between the two extremes, between those two gaps. If you move to J90, then the enumeration starts to become really impractical. In this corner, you can basically do nothing. The mean flow got worse, but not much worse than it used to be, which is very good. It means we can scale well. In particular, we are solving to optimality the left-hand side always. The envelope, interestingly, now shares a lot of the difficulties found by the enumeration approach. And this was kind of a surprise to me, but actually this was happening. Okay, the second important question is, okay, when we don't reach the timeout, what happens? How good are the mix spans that we are going to obtain? So now I will be comparing gaps. By gaps I mean, I take for each instance the best solution between the three approaches, and I measure the percentage gap. For each approach I measure the percentage gap from the solution found within the time limit and the best solution found for the instance by the three approaches. If no feasible solution is found, I count the 50% gap, because I cannot show you too many graphs, so this is a way to count the number of non-feasible solutions found. So for J30, all the approaches are working pretty well. The mean flow is slightly worse than the others. We have a bigger gap, but this is not too much. Still, it is pretty good. If we move to J60, then we realize that the enumeration approach has a lot of difficulties, of course, as before with this corner. The mean flow has a bigger gap, and the envelope is very, very nice here. Even if we don't prove the optimality, we are able to find very good solutions. If we move to J90, then the enumeration, we already knew this, becomes really practical. Those are huge gaps, meaning that many, many times you don't even find a feasible solution. The mean flow is getting worse, but just a little bit worse, and the envelope starts to have a lot of problems. So, to summarize, we introduced a new method for clinical and critical set detections for residence constraint posting. The method is simple, is fast, it is nice for several reasons. We have performed an extensive comparison of state-of-the-art conflict detection methods, and the interesting result is that the three methods appear to have complementary strengths, and also the problems where they behave well and where they behave badly, they are pretty well characterized. You can really look at the resource strength and factor, which tells us that there is a lot of work that we may consider. For example, hybridizations. Is it possible to remove the enumeration from the X procedure to the envelope procedure to make it more scalable? If we have a regular cost function like the make span, it is possible to exploit this irregularity. And there are a couple of ways to do it in the literature, and they work pretty well. But if we have a more complex objective, in principle, those general methods that I showed to you may be very interesting. Say you have to minimize earliness and tardiness costs, right? You know it's very difficult to do it in the classical scheduling procedure. But if you have just a temporal network, you can minimize the tardiness and the earliness with the simplex, the polynomial time. So in principle, this kind of approaches may be very well suited for that kind of problem. Nobody has attempted that so far, so this is maybe a very interesting research topic. Second, if you take this kind of approaches, you can take scheduling. If you take this kind of approach in a problem where you have durations depending on the decisions, you may be able to take scheduling decision before the durations are known, which may be in principle very nice. We have a better merging between the allocation and the scheduling part, which is usually difficult to obtain. Another interesting topic is developing perhaps a special purpose propagation algorithm that take advantage of these kind of ideas. For example, you could use edge finding to actually detect edges instead of just pruning the time windows. So I'm done, probably a little bit over time. If there are questions.